Hello, my name is Gavin Diaz, and join with me are Pooja Ladd, Stephanie Paintshaw, and Carolyn Power, and Rebecca Serralta. And this is our AI Medical Diagnosis Assistant project for Capstone 2. Thank you so much for joining us, and let's begin. The problem that we wanted to bring to attention was how diagnosing genetic diseases often requires multiple tests, manual interpretation of symptoms, and specialized genetic expertise. Patients may present incomplete or vague symptoms, therefore, clinicians must compare thousands of possible conditions, which can lead to delays, higher costs, and limited access to accurate diagnosis tools. Therefore, our project addresses this challenge by developing an AI-assisted diagnostic system that analyzes patient-reported symptoms and optional VCF-encoded genomic variants to efficiently predict the top probable conditions. As we can see here, is a list of the three core data components. The first being human phenotype ontology, also known as HPO, and this essentially encodes symptoms using biomedical standards, which will also include names, synonyms, and a hierarchical classes. The second data component is the disease knowledge base. These are core phenotype terms for disease, as well as known pathogenic RSIDs, and this is used for symptom similarity and variant evidence score. This brings us to the third data component, which is the synthetic patient cohort, which is many cases used for the model training, and each case does include phenotype profiles, disease lead variants, and background genomic bias. Here we can see our design. Ideally, the first step is when the user does select a symptom, which leads us to the second step, where they will have the option to select a sample VCF. The third step will be where the front end sends both information to the back end, which brings us to the fourth step, which is where the back end will normalize symptoms, extract RSIDs from VCF, and it will also run integrated classification pipelines. Finally, this leads us to the fifth and final step, which where output top ranks, such as confidence scores and an urgency level. Here we have our tech stack. The front end consists of JavaScript, HTML, and CSS, and our backend consists of Python, where we use a fast API, the Python framework, which is used to build our API, and as well as scikit-learn library for our machine learning model. The backend logic consists of a prediction engine that uses three signals. The first being the model probability, which will show diseases, the likelihood of a disease learned from synthetic training data. The second being variant evidence, which is where we will check if VCF RSIDs do match pathogenic variants for diseases. And the third signal is the symptom similarity, where we use Jacquard overlap to measure between user symptoms and each disease profile from the KB. Of course, we have our healthy case logic, which will be triggered when symptoms are minimal and common, and the VCF is benign and or neutral. Here we have an example case of JSON file, the case used to train models. So as we can see, we have the case ID, the disease, label, severity, when it was created, the HPO terms, and the VCF file. Next are the test case validations. Test case 1 is symptom only input. Therefore, the only expected input from the user is the symptoms such as weight loss. The expected result will be a low confidence due to non-specific symptoms. And the final result will be the system spreading confidence across 5 probable conditions. Test case 2 involves symptoms and VCF input. Therefore, the expected input from the user will be once again these symptoms, for example, weight loss, as well pathogenic variants, the VCF. What is expected is a higher confidence and clearer condition mapping. And the final result will be the system identifying the top 5 likely conditions with increased confidence. This leads us to test case 3, which is healthy control. The input would be very few symptoms along with benign VCF. And what is expected is for the user to be classified as healthy. The final result will be the model returning the healthy result with bounded confidence. A few of the limitations that revolve around this project, the first being the data and evaluation bias. We did train and test on a limited curated data set, not on real clinical data. Second point is simple symptom matching. Our project does not exploit the full HPO graph, and synonyms and free text patient descriptions are not handled properly. The third point is this has not been clinically validated, and it is not a medical device. No comparison to real doctor diagnoses. There have been no user studies, regulatory review, or safety checks, and this is only intended as a proof of concept decision support tool. And this brings us to the future work, which is stronger data and evaluation in the future. We would like to collect or simulate more diverse, noisy, and realistic cases, and as well add external test sets to measure generalization and avoid overfitting. We would also like to include a couple of UI improvements and some sort of explainability for the users. We would like to show which specific symptoms contributed most to each prediction and show which genetic variants influenced each disease, as well as adding visual breakdowns for different results. And lastly, we would also like to implement some sort of security, privacy, and clinical integration. We would like to add some sort of authentication and request logging and enforce stricter handling of VCF uploads and evaluate with clinicians in a controlled environment as well. Overall, we have developed an AI-powered diagnostic assistant for analyzing HPO-linked patient symptoms and optional genetic variant data. This uses a random forest model combined with phenotype similarity scoring and variant level associations. This predicts the top 5 most likely conditions with confidence scores, supplements predictions with clinical context from public medical data sources, and this is designed to support faster and more reliable early stage diagnosis, especially for vague or incomplete symptoms. This is brought us to the conclusion of our intro video, and please feel free to view our demo video. Thank you so much and have a great day. Bye-bye.